Hey everyone, today we're gonna be redoing this problem that I got right the first time but was awful at explaining. Very non-rigorous methods, bad terminology, so we're just gonna be redoing it with a bit of a better method today and showing what this series converges to. So speaking of the series, we have the series as n goes from 1 to infinity of 2 plus 1 over 10 to the power of n plus 2 over 10 to the power of n plus 3 over 10 to the power of n all the way to 9 over 10 to the power of n, and we want to see what this converges to. So for my first thing is just evaluating these fractions at 1. 2 is a constant, so we're actually going to bring this to the outside of a summation, but we're gonna do that after we evaluate essentially another constant when we evaluate these fractions at n equals 1. So that would be, 1 over 10, 2 over 10, 3 over 10, all the way to 9 over 10. And if we pair up these fractions, so, oh right, I'm here. So if we pair up these fractions where we add up 1 over 10 to 9 over 10, 2 over 10 to 8 over 10, 3 over 10 to 7 over 10, and 4 over 10 to 6 over 10, we get 4 pairs of 1, which is just 4, and then we have the 5 over 10 left over, which is just 0.5. So we, in total, when n is 1, the fractional part of the sum comes out to 4.5. Now this is now a constant, and so we can bring that also to the outside of the summation, combine it with the 2, so we would get 6.5 plus our sum as n goes from, we're going to continue to keep n at 1, and I'll show you why in a little bit. Well, the reason why we keep n at 1 is because we're not going to rewrite our sum. We know that the fractional part of our equation is, at least when n equals 1, 4.5. And so what we're going to do is we're going to have 4.5 over 10 to the n, because we've taken out the constant part. We've already evaluated at n equals 1, so instead of making it n equals 2, we take what n equals 1 was, which is 4.5, and we put it over 10 to the power of n, which removes the need to change our starting sum value from 2. So we can leave it at 1, because if we put it at 2, we get a slightly smaller number, and that's not what we're looking for, because that's not the right answer. So now we have our constant, we'll just label that C, brought to the outside, and we have what we're going to turn into a geometric sequence, essentially. So 4.5 over 10 to the power of n can actually be rewritten as 4.5 times 1 over 10 to the power of n. And like I stated previously, 4.5 is a constant. However, this time when we bring it to the outside of the summation, we're not going to be adding it to 6.5. Well, we are, but we're first going to do order of operations. We have to multiply it with our sum. So this new sum becomes 6.5 plus, and we'll put a parentheses here, 4.5 times our sum as n goes from 1 to infinity. This time, since we've taken out the 4.5, we have just the 1 over 10 to the power of n. So now this is our new series, and as you can see, 1 over 10 to the power of n, this is just a nice, easy geometric series to evaluate. So when we plug in 1 to 1 over 10, we get 1 over 10. So I'll write the formula for the geometric series here. So S is equal to A over 1 minus R. So A is our starting value, our first value. So when we plug in 1, our first value becomes 1 over 10. R is just the common ratio, which is also 1 over 10. So ultimately, plugging in, we would get 1 over 10. Oops, I screwed up. We would get 1 over 10 over 1 minus 1 over 10. This comes out to be 1 over 10 over 9 over 10, which becomes, what is it, 10 over 90. 10 over 90. And since I have everything evaluated as a decimal, we're just going to plug this into a calculator. This one's pretty easy to figure out. You don't have to use a calculator. It's just easier for the exact value. So now we have 0.1 repeating, right? Now we have essentially what this part of the sum is to be 0.1 repeating. We're going to multiply that by 4.5. We get 0.5. So now we have this times 4.5, which gets us 0.5, and now we can add it with 6.5. So 6.5 plus 0.5 is obviously 7. So now we have just shown that this series converges to 7. Bit of a more rigorous method from my last video where I said it diverges but approaches 7. But here is a much better method to show how this series converges with a little bit of summation, like manipulation, I guess, freaking out constants and splitting up terms to make an easy geometric sequence. So yeah, thank you for watching.